I've been involved with the Exascale Computing Project since about its very beginning. I've been the Director of Software Technology for the effort since October of 2017. It's been a train ride and a tremendous experience, life experience, and I think we've done a lot of very interesting work. It's one of the biggest projects that DOE has sponsored in anything, but especially in software. And so the ability to produce applications and libraries and tools in this space and leave that as a legacy for the rest of the community is a big part of what we're trying to do here with ECP. Now, we've reached the end of the project. We have our final review in April, and the next things are coming along, and that's what I'd like to talk about during my presentation, but also afterwards if there's interest on your part. So we've delivered Frontier, and Aurora is accepted. El Capitan is coming along. These are real systems based primarily on GPU architectures that are not NVIDIA. So we're trying to grow the ecosystem of available hardware software stacks to diversify what's available to the community as we go along. This is a beautiful set of images about the applications that have been impacted. There were dozens of applications, some of them which were mature, others which were just getting started, and some in between. All of them have been delivered on the exascale systems with incredible performance and scientific advances. Underlying those applications is what we call E4S, the Extreme Scale Scientific Software Stack. Is what Samir will be talking or leading as a workshop on Thursday. It was born out of ECP. So it was developed, conceived, and produced under ECP and will continue on for a long period of time as our efforts in post-ECP continue. What is it? Well, in one way, it's a SPAC script, if you're familiar with SPAC. It's a recipe for building a bunch of products that are version compatible, but we do a lot more. We test it, we put out documentation, we provided a container forms, it's available on cloud services. So in lots of ways, it's a ready-made stack of libraries and tools for HPC and AI capabilities. We have these beautiful build caches that can dramatically reduce your build time by a factor of 10 or more if you're rebuilding the stack. So lots of beautiful features associated with E4S and the efforts, and support as well for its use. One of the great things that ECP had was an industry and agency council. These are people we met with, a bunch of you are in this room. As we went through the project, we grew these relationships with our agency and industry partners. We would tell them what we're working on, get advice from them. We would grow together an understanding of these GPU-based computing systems and some really beautiful relationships that developed out of that. And that's actually why I'm here, is because of those relationships that we established, and we want to see them keep going as we go forward. So ECP, the bottom line is we've successfully delivered the exascale systems, Frontier and Aurora. We have all these beautiful applications that run on it. One of the great things for DOE, and I hope for the community, although this community already knows this, I think, the energy efficiency that you get out of using GPUs is really incredible. It's a way for us to get the performance that we need at the very high end. And we have thousands of users who are already benefiting from these systems. Frontier has the highest availability and the highest usage rate of any system that Oak Ridge has delivered, and in part it was because of all the effort that went into making the software and applications ready. All right, so for the rest of the talk, I'm going to talk about one piece of ECP. There was three focus areas: application development, hardware and integration, and then the software technology areas, which is where the libraries and tools were developed that I've led, and Samir led technically in lots of different ways. So we'll talk about this specific piece. All right, what did we work on? I said all these libraries and tools. Well, here's a sampling of what we worked on. These are things that you know about. We invested in two MPIs, MPI-CH and OpenMPI, providing funding and interactions with the vendors that allowed us to support these MPI libraries for the big GPU-based systems, Frontier and Aurora. We worked on OpenMP, OpenACC for markup approaches, because some of our applications needed that. Performance portability libraries. I'll talk a bit about Cocos and Raja. Those are two of the big outcomes from ECP that grew up as part of ECP. We did a lot of investment in LLVM, vendor compilers. The best way to get software supported is to not have to support it, to give it to somebody else whose job it is to do that. Performance tools, PAPI, Tau, HPC toolkit. You see the two of the authors right here. And then math libraries, BLAS, sparse solvers and such, all of these things. And then I/O capabilities, data compression libraries, and Viz as well. So these are all things that we worked on under ECP, getting them to be portable and performant on exascale systems. And that really is the legacy of this activity, is the portable performance across these GPU systems. All right. So let's talk a little bit about this portable performance. If you're in this field, you understand, these are kind of 4 basic ways to do parallelism for accelerated devices. One is you just write kernels using the native environment. The others, you try to use loop pragmas, but these are still immature, right? If you're a Fortran user, this is really the only in-language way you can get access to these capabilities. C++ abstractions have ended up being the most popular way among our ECP applications to get portable performance on GPUs. And then co-design frameworks, which also then use these C++ abstractions underneath. So these are the 4 ways that our application teams try to get performance portability across the various systems. And so you can see in this slide that there was a shift with ECP away from Fortran to C++ to some extent. The teams that could afford to and had the skills would actually migrate it away from Fortran as a part of their ECP activity. C++ and C were the dominant languages, and then some amount of Python as well. And these are all then, on the right column, all the different ways that people programmed. I'm going to talk primarily about the Cocos version because that was the most popular and seems to be a way that going forward that a lot of people find attractive for doing this kind of portable parallelism. Cocos is an abstraction layer. It's a C++ template metaprogramming approach to doing node-level parallelism. It abstracts both the execution iteration count and the data association, the storage association. So you can express an algorithm independent of how the loops are traversed, and you can express the data structures independent of the storage system underneath. And so you can remap data. And so it abstracts both of those things away from you as the domain scientist, but then it compiles down to an appropriate layout and an appropriate iteration strategy depending on the kind of device you're running on. It's been used in a lot of settings. It started off as a project at Sandia, but has now emerged to be something that is widely used across many institutions. And in fact, a lot of the development is now done at other institutions that are not Sandia. So it's one of the big successes of the exascale computing project that we have this portability layer available to us so you can write code once and compile it to many different platforms, including future ones, as long as there's a nice concurrency aspect to the processor you're trying to work on. This is one of the codes, LAMPS, which is widely used. I have one more slide at the end about LAMPS. They've had a lot of success in portable parallel execution using Cocos. This is another code, a newer code, XGC, that was rewritten from Fortran into C++. They also used Cocos and were able to get very good portable performance using the Cocos layer. So in some ways, what we're starting to realize at the DOE computing facilities is, we've asked the vendors for performance portability for a long time, but they always want to invest in their own custom approach. And so by providing these portability layers ourselves, which in turn then use the vendor's specific CUDA or HIP or SYCL, we've in a sense achieved this portability that we've longed for. And you don't have to use it for every single kernel. If you have a specific kernel that needs to run really fast, you can write a custom version of that for CUDA, for HIP, for SYCL. So it allows you to also blend the approaches from highly customizable to more generic approaches. And we also have efforts going on for HIP Aurora, SICL on Frontier, and these are other approaches, and these may pan out as well. We've had some success at that. But so these are two different approaches now that allow us to consider in a serious fashion performance portability across these different device architectures. All right, a little bit about performance portable libraries. This is just one example. We have lots of libraries, math libraries work going on. This is in systems engineering to develop a solver that could do sparse indefinite, symmetric indefinite systems. Not something that is commonly found in the open community, but one of the efforts was to create in the library called Ginkgo, a performance portable library that runs across all of these GPU systems. So that's just one example of the many efforts in the math libraries area. And then one effort in the data area is a compression library called ZFP that does data compression in memory, provides a lot of nice functionality, portable functionality across all the different architectures because, again, as with every high-end system, I/O performance improves, but not nearly as much as compute performance. And so these are just a few examples of all the different libraries and tools that we worked on under ECP. And they're all generally available then via E4S or through the vendor stacks. All right, so just a little bit of a summary. So we have all these libraries and tools. They're being supported going forward. They work on a variety of platforms, including CPUs too. We have a cluster called Frank I'll mention a little bit about that has Grace, and Grace Hopper nodes. So also we're porting this software to the next generation of NVIDIA hardware. The use of portability layers means that a lot of products are already poised to work on future platforms. Then this next point is that regardless of what the application is using, if the application wants to use CUDA, our performance portable libraries will support them in that. If they choose a different HIP, if they choose OpenMP, we can support whatever the application chooses, we can support them for these. So we've had some really good outcomes from this effort in ECP and performance portability. I want to talk a little bit about the software ecosystem, E4S and SPAC. For many decades, DOE's been investing in the development of libraries and tools. That's not new. What is new is our aggregation. We produce two layers of aggregation. One is the so-called SDK software development kits. These are collections of similar products like math libraries, like I/O libraries, where we bring people together so that they can share best practices, share knowledge that they're gaining about how to use these systems, how to design software for them. That's the SDKs. And then the top level is E4S, which is the aggregate collection of the entire portfolio. And so these two layers were a big part of what ECP did to deliver software. Of course, we did this using a tool called SPAC, which allows us to manage and build software on a huge variety of systems. I'm guessing there are a number of SPAC users here. I hope that's the case. If not, you want to find out more, we're happy to tell you. It's been a great boost for us in terms of productivity. All right, just a little bit about SPAC. Started in 2016, grew in its capabilities, continuing on into 21, into 23, and now this is what it's like right now. And just to show you the comparison, this was what it was in 2016 and now today. And so SPAC has taken off as a way to build software. You still use CMake, you still use Auto Tools, but you build a SPAC recipe to build your product and tell it what products you depend on, and then it can recursively continue to build these products and build it in place and supports a whole bunch of good usages. Thousands of users worldwide. E4S, I mentioned, supports it. So we support about 120 products directly, but then of course we have to build hundreds of others. And SPAC is what we use to build all of those other libraries and tools underneath. This is a screenshot from a website we run, dashboard.e4s.io, that shows you the builds that we're producing for the various systems. So you can see Perlmutter, which is an NVIDIA-based system, and then the exascale systems, Aurora and Frontier. Sunspot and Polaris are two other HPC systems. You can see the dashboard of our builds and what's working or not in the various programming environments. This is for the ROCm stack at AMD. This is for the CUDA stack. And then for Aurora, we're still bootstrapping a lot of the libraries and tools efforts, but we're continuing to make progress on Aurora, the Intel-based system. Frank is a new development for us. It's a system, we call it Frankenstein. It's got this massive file system and all sorts of many different types of device architectures that surrounding it, so you can clone your code down to Frank, the file system, and then make it portable and do CI testing. We're up to more than 6 million CI builds, I think, on Frank right now against all of these different devices. So this is how we as software developers keep our software stable as we go forward. And this is just a little bit highlighting of the kinds of things. And this is where the Grace and Grace Hopper nodes are. One of the key things that came out of ECP was to try to expand our business model. Before ECP started, local teams at a local lab with a local facility would trust the libraries and tools. If you're an application developer at Argonne, you would trust the libraries and tools that were available from other Argonne developers on Argonne systems. But it'd be a lot harder for you to trust libraries that came from a different lab or a different facility and trust that you could run your software on any of the DOE systems. What ECP did was it allowed us to expand the scope of trust. And then also we could expand the scope of cost and benefit sharing, right? We could share each other's software across all these facilities and get the benefit from that and amortize the costs associated with that. Then we also brought in a business partner, Paratools, and brought them in to support us at a commercial levels. In fact, they support the DOE facilities to use E4S. So we bring in a third-party company who specializes in support of these libraries and tools. Also, it allows us to talk with other US agencies. They can use E4S because they can call Paratools to get support. Industry companies who want to use E4S can do that and get support for it. And so bringing in these new business models were a really important part of what we tried to do with ECP. And then, of course, and I'll talk a bit more about this, the High Performance Software Foundation, which is pretty new. We just announced it at Supercomputing last November. And this is the next way that we want to expand cost and benefit sharing for our software capabilities. I want to mention that there is a pro version of E4S sponsored by Paratools, so you can go out and get a copy of it and use it. This is sponsored by DOE's SBIR program. And now I just mention a little bit about HPSF. So if you're familiar with software foundations, Linux Foundation, there's NumFocus, there are other software foundations. We were looking for a way to broaden our ability to collaborate with entities that were not in DOE and entities that were similar-minded, but there was no way to share funding. There was no way to have other people invest in our software. And so Todd Gamblin and Christian Trott are two leaders in this space and have stood up this High Performance Software Foundation, HPSF, which is a Linux Foundation umbrella organization that allows us to then bring in member teams and expand the ways that we can collaborate, especially with industry, especially with agencies, especially internationally, to support the development and use of our software and make it really robust, really available, well-funded, as we go forward. And so we look at the HPSF as being an opportunity for us to be really serious about open source software in a way that we haven't been before. And so it's one of the legacies of ECP that we've reached this point, and one of the things that we expect to see going forward. In addition to HPSF, we've had a lot of interactions with industry and US agencies. Some of our best interactions have been with our agency partners who have similar code situations where they want to transition to GPUs and they want to leverage and learn from what we were able to do in ECP. One of these is a standalone study done by the DoD HPC Mod Office using E4S. They didn't want our help. They went and grabbed the code, they grabbed it, they looked at the documentation, they tried to do it on their own, and they had a lot of success. They were able to get Flux as a tool and install it. Never used it before, can use it from user space. That's one example. Tau, they were able to get it and use it easily from E4S. Cocos and Raja, they didn't have performance portability layers on their GPU systems. They were able to install that and run the tests and see the performance improvements from using it. And then the last one that I think is really cool is LAMMPS. They use LAMMPS a lot. LAMMPS is an MD, molecular dynamics code, very popular code. Not only were they able to install it easily and run it, the installation that they got, because they used our build recipe from SPAC, one that was developed by the LAMMPS developers, they were seeing a runtime of LAMMPS. LAMMPS itself was running twice as fast as their private installation ran. And so this is, again, the power of these kinds of aggregation and benefit and cost sharing that comes from having a software ecosystem. And again, they did this all without our help. We were really elated to see this when they showed us these results in January. All right, so going forward, so ECP is ending, right? In fact, I'm one of the few people still funded by ECP. All the developers have they're part of post-ECP efforts, but I'm still drawing a paycheck from ECP. Okay, so this is a slide, and this is not hand-picked, of some of the applications that we used as part of ECP. And I just look at the circles and see the improvements. Now, these are not exactly speed ups, strictly speaking. They do science scaling as well. But you can think of it as speed up. And every team was supposed to get 50 times improvement or more. Look at some of these eye-popping numbers. Right? These are not hand-picked. This is really across the board what they were seeing. Well, I have to say the 34, 67. Nobody else got that. But everybody else did in the hundreds, right? And so, and what we want to be able to do is realize the same potential with a bunch of other apps. And so what post-ECP is largely about is helping other people realize the same potential going forward, because there are hundreds of other applications in DOE space and in other spaces that can realize this similar kind of benefit. It's not just about getting GPUs underneath. It's about re-architecting, exposing concurrency, having lots of help to get the performance out of it. But all of this is possible if we go forward and invest in these other codes going forward. So what we want to do is exactly that. Right, so what we're trying to do post-ECP is realize this 100x potential. Okay, so this is my attempt at marketing. I've been using this term 100x. I don't know. It seems to work okay. Again, I'm not good at marketing. I'm not good at joke telling, but it's our attempt. All right, so we've spent 7 years building this accelerated cloud-ready software ecosystem. And we're positioned to use GPUs from lots of all three of the major vendors. We've emphasized software quality. ECP gave us the headroom to focus on improving software quality, and that tradition is building within the DOE ecosystem. We have people who care a lot about good testing, good documentation, making sure that the code is usable by others, that it's designed well. These are all important things that certainly we cared about in the past, but we have better skill and better prioritization of these activities now. These portability layers that we have are really important. They allow us to avoid vendor lock-in. They allow us to adapt to whatever comes along. Data flow architectures, we have a leg up moving towards data flow architectures as an example. And so we've been able, because of these investments, to lower the cost and increase the performance for accelerated platforms. And outside of AI, and this community as well, I realize you have embraced GPUs for many years, but in the broader scientific community, we don't see GPUs as heavily used. And we see the work that we've been doing within ECP as a way to help other people bootstrap and de-risk their efforts. By knowing that you can have dozens of different applications that all run like this, it's at 100x or more, that de-risks the path for other people who want to do it. And so we think that this is a path and performance portable software ecosystem for others to leverage. Okay, we also did AI/ML. There's within E4S. We've got on the cloud. We haven't done quantum yet, but we see that as just the other attached device with a different ISA and a different instruction a path, a software stack. And so we don't see that as fundamental. So we see E4S as being the place to grow these other capabilities as we go forward. And this is just showing some of the libraries that are available in 24.02, the latest release of E4S for AI/ML. So a little bit about the future. DOE sponsored these seed projects in the fall of 2023. And these then are growing into larger projects. I am leading the project called PESO, which is the aggregation of the collection of capabilities and has the responsibility for E4S and SPAC development. Most of these other projects are dealing with specific things like math libraries, like data and I/O, programming systems, and so on. So they're focusing on a specific domain, and then we're integrating those into what PESO is doing going forward. This is just a schematic of what PESO does, and you can see we're doing partnerships, services, and then E4S and SPAC as products. And why I'm here on behalf of PESO is because we have engagement with commercial companies, US agencies, and industrial users. We also care about software quality assurance and security. That's another aspect of the work that we're doing under PESO. This is an eye chart of all the team members, but what I want you to see is that all of these team members who are part of PESO are also members of the other organizations, the domain-specific ones. So what we're doing is we're bringing people from those smaller specific, domain-specific teams and making them members of PESO as we go forward. All right, so final remarks. So we learned a lot about producing software contributions to the HPC community in all these different ways. We want to continue and expand these efforts going forward. We want to realize this 100x potential across a bunch of other codes. And we want to work with the HPC community, including this community, as we do so, especially via the E4S activities and the High Performance Software Foundation. And we're looking forward to future conversations. And thank you for your time.
This might be a naive question, so excuse me.
I like those kind.
But you know, it's looking like at DOE and elsewhere, the architectures are moving toward a more modular kind of an approach where you might have, you know, a simulation, general simulation machine, and then AI acceleration piece, and then soon enough quantum.
Yeah.
How much work is going on to help know what parts of a workload to assign to which pieces of such a system?
Yeah, that's a good question. I mean, each facility has its own, you know, suite of applications that it tries to anticipate will be a good representation of future workloads, but it really varies from facility to facility. I don't know of a general answer to that other than that they do quite a bit of homework in that space at each facility to do that. Oh, well, no, I'm not aware of any myself. Okay, sure.
7 years is a long time.
It is.
A lot of things have happened in the meantime, including what we've heard about this morning, AI.
Yeah.
If you had the opportunity to go back in time, redo the project, what would you do differently?
We're writing a book on that. And we really are. What would I do differently? Well, we would obviously incorporate AI from the beginning, right? The ECP started just before we were at least aware of how important AI would be. We introduced AI projects into the mix, but it wasn't baked in from the beginning. So we would have clearly done that. It took us a few years to kind of work out the dynamics of working a cross-lab, cross-institution project but we have lots of lessons learned there, some positive and some we wouldn't do it that way again. But communication is huge. Leadership is huge. We had Doug Cothey was our leader for much of that period of time. Fabulous leader, if you know him. Lori Deitchen finished off also. So leadership is really important as a part of that. So those are just a few things. But buy the book.
You had a lot of academic partners as
Yeah.
part of the
Yes.
ECP program. Is this ending of the funding? Is the ending of the funding it's a financial cliff for them? Are they going to lose some of their grad students and all that? And
Yeah.
you know,
Sure, sure. So ECP was an unusual amount of funding over an unusually long period of time. Post-ECP is less funding. It's not completely missing, and we have plenty of university partners, but we're not funding it at the same level as we were under ECP, and it is painful. It has been painful. The transition in funding. It's in part also challenged by budget issues. At the federal government level, the lack of a budget has made things really hard to manage as well. At the same time, Peso is funded at $4 million a year for the next 5 years, and I like that. And there are other projects are being funded as well as part of that, and so we have a path forward, and we hope to grow it. But the best thing we can do is do excellent work and hope for the best after that.